Wow. 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 Wow, he's sniffy. Hmm. Hmm. You sniffed. You sniffed. Wow. 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 Um, Stop it. You sniffed. You sniffed. Wow. Explore the relationship between the selling prices Y and the appraised values X of the 48 homes and file by estimating a simple linear regression model. Interpret the standard error of estimate and R-squared and the least squared line for these data. Is there evidence of a linear relationship between the selling price and the appraised value? If so, characterize the relationship. Is it positive or negative? Is it weak or strong? For which of the three remaining variables? The size, number of bedrooms, number of bathrooms, is the relationships with the home selling price strong or justified? It's weird how for that one unit, she actually posted the answers to some questions. That was funny.
Good morning, everyone. Make sure I get the problem number right. Chapter 10, number 1. It's appraised PO2. Estimate a simple linear regression model, and I interpret mean your relationship size level home selling time. So we're going to be using the data analysis tool back again. And we're going to go down, select regression. There is only one regression option, so it makes it simple.
Regression. You sniffed. Data. Data analysis. Regression. Input range. Oh man.
And the home selling price
Y and X. Selling price. Selling.
According to the problem, work was supposed to be the appraised value.
The Y range is the. What? Wait a minute. Are these in a different order? Hold on a second. They said appraised values.
And the X range, according to the problem, work was supposed to be the appraised value.
Selling price is the Y. I could have just looked in the problem, but I didn't feel like it, so too bad. Labels.
B. I do have my labels in the first row, so making sure that's checked off. My output right on this sheet here. In chapter 11, we'll start.
Oh no, chapter 11. Chapter 11.
Start looking at some of the assumptions, so we'll be using some of these options down here then, but until now, this is all we need, so go ahead and click on OK.
Oh jeez. I think I'm going to cut and paste it because it's not quite fitting on the page. And oh.
Expand All right. So the main thing is that they asked us about the strength and the direction of the relationship. This is the Pearson correlation coefficient. We first talked about Pearson correlation coefficient in chapter 3, right? And it's represented with a small r for a simple linear regression. For a multiple linear regression, it's represented with a capital R. Thus, Excel's obtuse way of using multiple capital R to represent the correlation coefficient. So this correlation coefficient is greater than 70%. Oh, it changed my R. I don't want you to do that. It's greater than 0.70, so it's a strong relationship.
Ooh. Pearson. Ah! How do you undo that? Right. More than 0.70.
It's a positive relationship. It when we look down here at the appraised value, this is a positive 0.93, so it means that we're moving up to the right.
What?
The next thing they asked about
I'm
was
so confused. And it is positive. I mean, what is this number as opposed to this number? I mean, if it was a negative, wouldn't this number be negative? I don't know.
the r squared. Oh, and we'll get to SE next. R squared is the goodness of fit.
Goodness
and what
of.
the goodness of fit is saying that here we have 69 point.
I'm just copying what she's writing. I don't feel like doing actual work right now.
Basically, so 69.5% of the variability in the home selling price
The home selling price.
is explained by the model, which again in this case the model simply is the appraised value.
It's explained by
Start,
space value. I have to do so many problems.
in multiple regressions, when we have more than one statistic, you would just state that the regression model explained by the regression. All right, so that's pretty good. it's almost 70% of the variability in the selling price is explained by the appraised value. So that only leaves about 30% that's unexplained by other things like possibly, neighborhood or proximity to certain things, school districts, something like that. All right. Standard error of the estimate, SE. Okay. And SE, standard error of the estimate, technically that should be subscripted. Now again, if you were on an exam or something, would I expect you to know this? In fact, you would just write the standard error if you needed to. But again, I need you to understand what SE is since the book keeps referring to it. So since SE is equal to 7970, that means that
Standard error. Whoa.
68% of the data. And where am I getting that number? If you remember the empirical rules, so 68% of the data was within one standard deviation of the mean.
68% of the data.
And since we're not dealing with a mean here, we're dealing with a regression line. You say within one standard error.
Falls within one standard error.
Of the regression line.
Well, the regression line.
So that's kind of abstract. It doesn't mean a whole lot, like, in my head. So just round it to $8,000. So we're saying, plus or minus $8,000 on either side of that line is 68% of the data. Is that a good fit or not? That's hard to say. Standard error becomes much more easy to understand and much more relatable when you start making predictions, because you're making a prediction saying, okay, for this particular, in this case, appraised value, what is my, on the next part of the problem was asking, so is it a significant relationship? Well, this middle table of the output, it says ANOVA on it, is the test for the model as a whole. So significance F is really the p-value. Okay, so this is what we've been calling the p-value. Again, I wish that instead of significance F, Excel would have just called it a p-value. As you can see, the F is extremely large at 332. That results in a p-value that's very, very small. This is 1.976 times 10 to the negative 39. Again, what that means is that there are 38 zeros to the left of that 1 and after the decimal. So it's 0.0000036 times and then 197. So an extremely small p-value. Very definitely less than, take a very small p value, 0, 1, or alpha, excuse me.
We can't reject the null.
Awesome. Well, what is the null? For every regression relation, linear regression, the null is not
H.
negative.
Oh, there is not a significant.
The alternative,
There's not. What the? There is not a significant linear regression? What?
Is there is significant.
What does that even mean? There's a significant linear relationship between
Selling price. Things that.
selling price and appraised value. My goodness. Oh, this is just problem number 1. Gotta be kidding me. I have to do 18 of these problems. Man.
Next part of the problem asks us which of the other remaining variables.
You know what once happened to me?
Better.
Dude, I can't believe this happened to me once. I don't even understand how this is possible. Because I thought final grades were supposed to be posted like within a few days after the final day of class. But at NICC, I once had a large project I needed to do for a class. It was due on the last day of class. And then I didn't turn it in. And then I asked my professor if I could have an extra week to do the project. And he said, sure. And then I turned in the project a week after class even ended. That's funny. But like, aren't final grades supposed to be posted like within 2 days after the end of the course, though? So it's not possible for me to do that in this class. Because I was just thinking, like, man, these problems are going to take so long. Can I even finish this on time?
Now it's a matter of going back in and running a bunch of additional analyses. Just switching out. Excuse me, my allergies are terrible.
So we've done everything in the problem except for the last part. We've done standard error, R squared, least squares line, linear relationship, positive or negative, weak or strong. Now we need the relationship between the selling price and the other variables. So selling price will be Y, and the other variables will be X, right? It's interesting, we didn't really make any graphs. We just did the tests. So I'm assuming for the other ones. Oh my gosh. We're probably going to need to do. I mean, how many of these are we going to need to do? Oh, 3 more. We need to do this thing 3 more times, but please tell me we don't have to write all this extra stuff 3 more times too, right? Man. I think all we need to do is look at this part right here and compare the p-values or something like that. I don't know. Or no. No, we probably just need to compare these numbers. These numbers right here. You sniffed. We're just going to say this is answers for A. And then we're going to do. We're going to do size of the home, and then we're going to do the number of bedrooms and number of bathrooms. Dang it. And I'm assuming that its selling price is Y, and then size of home is the X.
Alright, so we're going to switch the first, or the X variable, the first option that's left of square feet. And we do need to put this somewhere other than page 4. Let's drop down here. Page 3. Okay. Again, the main thing to look at to determine if it is.
I mean, it's not going to take that long. Well, you sniffed. Dude, I'm still on question 1 of 18 right now. You've got to be kidding me. And not to mention I have to do the Unit 4 project. Square feet. And that's it. We're going to put it in this one. So, I think we just need to look. I mean, for the rest of these, I think we just need to look at multiple R, right? Oh, God. Man.
This is a significant predictor is significance, and we see that that's got a
Significance.
level of 6.13
That's all we're looking at is significance of. Oh, ay, 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 ay. I'm going to be here all day.
And now we see again, it's significant, but the p-value is getting less. That makes any sense. It's now 4.2 times 10 to the negative 15. So we've gone from 39 to negative 15. Now, same time. And switching our x range out for bathrooms. And multiplication. So now we have 1.337 times 10 to the negative 8. So also significant. So how do we do that? Which is the relationship with the home selling price stronger? Okay. So the strongest one is the square footage, and one at significance level is very small. We see that the multiple R, which again numbers.
Oh my gosh, I thought they were asking compared all of them, including the first one you did. Dang it, what? Oh, never mind. It says for the remaining three, not for the first one, compared with the first one. It says, I mean, if we're looking at just the significance, I mean, can you look at both the significance and the multiple R to figure out the answer to that?
Which again numbers Pearson correlation coefficient. Numbers significant. Which is the relationship with the home selling price stronger? Okay, so the strongest one is the square footage, and one at significance level is very small. But we see that the multiple R, which again numbers the Pearson correlation coefficient. And it's greater than.
I probably could have done all of these on the same tab. Nah. I don't feel like it. That was funny. Number of bedrooms. Dang it! Come on! Why won't it just automatically select the whole thing? Like, seriously, you think triple clicking here would select the whole thing? You've got to be kidding. What the? Why is there an F? What is the F? Oh my gosh. Stop. 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 We ended up with numbers and numbers and numbers. The Pearson correlation coefficient is more than 0.7. is more than 0.7. So strong relationship.
Looking at the next one, the Pearson is down to 0.58, and the third one down to 4. So this one is in the strongly moderate, upper end of moderate, and this one is definitely moderate. Okay. So again, what does this mean? Collectively, actually, they might all be really good at predicting the selling price of the home. And trust me, this is not the last time we'll see this data set. We'll come back and revisit this as a multiple regression. All right. So that's the basics of linear regression. Those are the important factors there. If you look at my solution files, I tend to highlight with yellow the key things that you should be paying attention to and looking at. Oh, I'm sorry. The last thing that they said was to interpret the regression line. Here's a regression line.
Wait a minute, what? Where? Interprets the least squares line. The least squares line. Oh man.
Right here are coefficients for our regression line. So this is basically saying that the selling price is equal to plus
Selling price equals that number. That number plus that number times the appraised value. 0.938. You know what? 6023 plus 0.9384 times appraised value.
So when it says interpret that, that means that you're stating it like this, you're stating it in terms of words, or if you wanted to use like SP for selling price and AB for appraised value, you would just need to define those so that you knew what you meant or what they represent, right? And then the final interpretation is to say what that coefficient in front of appraised value means. So for each additional
dollar of appraised value, for each additional dollar of appraised value, the selling price increases by that number. 0.9384. Please tell me we're done.
that
Oh my gosh. Ooh. I don't care about the dollar sign.
Square feet coefficient can say for each additional square foot of home,
Oh,
dollars selling price increases by $47 basically. All right, so that's what they when it says interpret the model, that's what.
interpret the least squares line. Okay, thank goodness. Oh my gosh, this is taking forever. It took me 41 minutes to do the first problem. What? No!
So the next one is 10.5.
I'm not doing anything else. I'm done. I'm not going to type anything else. Oh, this is going to take forever. This is going to take forever. Oh. Oh. 10.5. This is going to take so long. Stop being slow. Oh, this is going to be the salary and years of experience. Years of education. Ooh. We have plenty of options for this. Ha! I canceled moves. We're probably going to need to find the. Okay, stop. Whoa! We don't need to delete that. We're just gonna do it on a separate tab, anyways. Please tell me it's not as long as number 1. Please, please. Examine the relationship between the annual salaries and the number of years employees have worked at the company. So the salary is Y and the number of years worked in the company is X. Examine the relationship between them. Interpret the least squares line. How well does the estimated simple linear regression equation fit the given data? Provide evidence for your answer. So it looks like it's going to be the same as number 1 except less work, so thank goodness.
Related for any of these two correlated years.
So they're going to do the same thing as before. Same thing.
Put this here.
All the same stuff as before. So, so we will put it on the new tab. Data regression This one is going to be, the Y is going to be annual salaries, and this X will be years employed. No? I think it's years employed, right? Years employed. Just double checking. Stop it. Stop being dumb. Dang it. Years employed is that one. So years employed, and the output range is going to be oh nope, it's going to be new worksheet. Stop being stupid. Stop. No! Undo. What did you just do? You can't undo what you just did? Seriously? No. Stop. That was fun. Can't I just undo everything? Come on. Come on. Stop. Stop. That's funny. New worksheet. Wow. It's the exact same. So for this, stop. It says just, I don't know, just.
The first thing that was asked is if the model is significant and to interpret the least squares line. So if
the p-value
is significant.
Conclude that there is a significant between salary and years employed. Conclude that there is a significant relationship between salary and years employed at the company. Stoppy.
Now the next part actually said to interpret the line again, so we're going to do that same thing we did before. So
Okay. Salary equals 28,394.5 1581 plus 1107.2184 times years employed. Salary equals that plus this times years employed.
Make sure it's either evident what it is or give a definition. All right. So again, what this is saying that for each additional
For each additional year employed at for each additional year employed at Datacom, the salary increases by this. The salary increases by 7.22. You sniffed. Is that it?
Part B, how well does the estimated simple linear regression fit? Going back up here, Pearson correlation coefficient is greater than 0. Years employed had a positive correlation, so
Greater than 0.7, so strong relationship. Did we get the same numbers? 0.7651, 5.93 to the negative 10.
for each additional year, raising the salary. All right, and our R squared 0.5854, so 58 point.
Do we really need to do that?
For very
Something percent of the variability in salary can be explained by 58.55% of the variability in the salary can be explained by the number of years employed by the number of years employed at data. Why do we need to do that one?
There we go. So basically then they talk about how well does the data fit. We're talking about the strength of the relationship and the goodness of fit. So we covered those two things.
Goodness of fit.
Some of these go faster than others, which
Two out of 18 done. 2 out of 18. Now we need to do number 7. Number 7. Number 7. Examine the relationship between the average utility bills for homes of a particular size and the average monthly temperature. The data includes estimate a simple linear regression equation. Interpret the least squares line. How well does the estimated regression fit the given data? How might you do a better job of explaining the variation of the average utility bills for homes of a certain
size equation fit the given utility bill by running. Did not like me.
Oh my gosh. So bills is Y, average monthly temperature is X. The average monthly temperature. It was that necessary? Yes. Great. Great. Just wonder. Oh my.
Right off the bat, my Pearson correlation coefficient indicates that it's a weak relationship. Only 12%, looking at the goodness fit, only 12% of the variability in the bill is explained by the monthly temperature, and then our significance is huge. 0.26, so that's really big. It's far greater than 0.05, so we're going to fail to reject the null. And basically, this model is a terrible fit.
Wait, let's see here. Did we get 0.26? We got the same numbers here.
But that can actually be explained pretty easily by
What?
I hate when Excel does this. If I'm going to do a scatter plot, I have to have my y variable on the right of my x variable.
I don't think we need to do that. We don't need to, do we? Please tell me you don't have to do it.
Scatter plot. And as you can see right away, what's going on here is that this is not a linear relationship. Right. So, and that makes sense, right? We have some months where it's cold and we're pumping in the heat, and this is for people who live in wonderful places like Wisconsin. We're pumping out the heat to keep our houses warm, and then the temperature gets into these nice temps that we're at right now, and you don't have to have the heat on anymore, and it's nice enough you don't have to have the AC on anymore, and you're getting some low bills. And then all of a sudden summer starts creeping in, and you start using the AC, and there's the utility bill. So the problem with this is that it's not linear. It's not saying that there's not a relationship between the two. It's just that it's not a linear relationship.
Are we supposed to put a thingy? Yeah, whatever, we'll do it. Dang it. And Excel is wonderful, so we have to actually copy and paste it here. So now we'll do insert a scatter plot, and there we go. And we'll cut and paste it here, and just put it like right around here, and there we go. Stop it. So I get it. This is not a linear relationship. Try a transformation.
This looks very much like a parabola to me. So if you could...
This is not a linear relationship. Okay, where do we put the answers here? Let's try to fit it up here. There. This is not a linear relationship. Try a transformation of the data. Parabola.
The right parabola or the right equation for that shape. I'm trying to make this. It's not something stupid. Anyway, and we use that mathematics on that. It would take that U-shaped data, make it linear, hopefully, or as close to linear as you make it. Okay, so that's one option. A second option is to actually use a non-linear. Use a non-linear regression. And that was funny. Bye.